Thank you, Brian. So Brian just showed you real HD video being streamed into TrueNorth chips, with the chips detecting and classifying objects in the video, then reporting those classes and the locations. So that's a hard act to follow. Thank you, Brian. Okay, so what I'm going to tell you about now is a little bit about how we program TrueNorth. In fact, we're taking a turn in the presentation at this point where myself and the next several speakers, the next half hour, we're going to talk about what goes into a TrueNorth program. And so I'm going to tell you the fundamentals of what makes a TrueNorth program. But first, we have to think about the chip. So we have a chip with 1 million neurons and 256 million synapses spread across 4,096 of these neurosynaptic cores. Okay, so what's in a neurosynaptic core? First, we have neurons, and these are the computational elements of the core, as well as the outputs. Second, we have axons. These are the inputs to the core. These receive spike events from outside the system or from other cores. And lastly, we have synapses. And these are the connections from the input axons to the output neurons. And one important thing to note is an axon here can connect to one neuron, all neurons, or any subset thereof. So we can make arbitrary connections from the axons on the right to the neurons, the axons on the left to the neurons on the right. And so we have a full bipartite graph here. Okay, so now I'm going to stick with the neurosynaptic core, but I'm going to look at it differently. So this was kind of an abstract way to look at the core. And now we're going to look at it more in a schematic way. So this is the way we hardware engineers prefer to look at the core. And again, we have our neurons doing the computation, our axons with the inputs, and then we have our synapses connecting axons to neurons. And so you can see that the synapses are organized as a crossbar array. And anytime there's a cross point between an axon and a neuron, we can put a synapse there and make a connection. And so we can implement any connection from axon to neuron. And so this is very much like a traditional neural network module. We have a small neural network with 256 neurons and 256 inputs. There is one constraint here relative to traditional neural networks. Traditional neural networks use floating point connections between neurons. Here we use discrete connections where we have a fixed point weight instead of a floating point weight. But as you saw for a lot of the demos, that doesn't make much difference. Okay, so I said I was going to talk about the program. So now we've gone through the basics of what a neurosynaptic core is. How do we program this? There's really two things we need to set in our core. First, we need to set the synaptic weights. So when an axon comes in, what does it do to each of the neurons? So we set those connections and those weights. And the next thing we need to do is we need to set the neuron parameters. So what does a neuron do when it receives inputs? Does it integrate and fire? Does it do some other operation? Is there stochasticity? Okay, but we don't want to build networks with one core. The examples Brian showed had thousands of cores, and we want to build systems with tens of thousands of cores as well. So how do we program those systems? Well, it's much the same because we have a modular architecture. We distributed all our neurons across these identical modules. We can program in the same way. So again, we set the synaptic weights from axons to neurons. We set the neuron parameters. And then one additional thing to build these larger networks is we set the connections between the cores. Okay, and one thing you can see here is this looks a lot like a traditional neural network that's bigger than 256 neurons. But now we have two constraints. We still have the discreteness constraint, and we also have the modularity constraint of the connections between the cores. Okay, so now, here is a network that's already been programmed. So we set all the synaptic weights, which you can see in the crossbars. We set the neuron dynamics. And now it looks a little different than the last one because now we have routers, the blue pluses. These are part of the routing network between the cores. And you see a bunch of red dots. Those red dots are just spikes in the system waiting to be delivered to axons in the core. So they're queued up and waiting to go. So now if I run an animation here, we can see spikes will be delivered to cores in the lower right. Neurons will integrate those spikes, cross threshold and spike, and then that neuron will send a spike into the network itself. This one is going west twice, then it's going to go north once, and it's going to be delivered into an axon and ready to be delivered to the core itself in the next time step. So here's the tick. We deliver the spikes, more neurons spike, and the simulation continues. Okay, so just to recap, for a network of neurosynaptic cores to program, we need the crossbar weights, we need the neuron parameters, and we need the connections from neurons to axons on different cores. Okay, now my colleague John Best is going to tell you more about the neuron parameters and how we program rich behaviors into them.
Thank you, John. So going back to the core, remember, we have 256 neurons. These cores are tiled 4,096 on a chip, and we can array a bunch of chips, and it all looks seamless together. And the basic behavior is spikes come in the axons, 256 of them. Based upon the connections set up in the crossbar matrix, they will flow down to the neurons. The neurons, based upon the neuron characteristics, will generate spikes. The neuron output axon is connected to one input axon on any one of the cores in the entire system. So that's the first thing we have to program is that connection matrix and where things are routed. In addition to that, you remember we had the description that we do things on a 1 millisecond time tick basis. The delivery of the output axon from a neuron can be programmed to be delayed from 1 to 15 of those ticks. Now let's look in more detail at the core itself, or the neuron itself. There are 23 parameters that can define the neuron. We'll start with the basic neuron that's an integrated fire neuron, which really forms the basis for most of what we do. Depicted on the top is, in the blue curve, is the single state variable for a neuron, which is the membrane potential. That's the thing that's accumulating up or down as spikes come in. There's a threshold that's depicted in the yellow dotted line, and the basic principle is that when the membrane potential for a neuron exceeds or reaches a threshold, that the neuron will then generate a spike, and it will reset. Depicted in the bottom, you can see we have a core, and this particular neuron we're going to look at in detail is connected to 3 input axons. And on this graph, we've shown a spike train input from the 3 axons that it's connected to. So in addition to just being connected or not to the inputs, we can actually assign a weight to those individual inputs. There are some constraints on that. They're 9-bit signed weights, and we can only have 4 different weights assigned among the axons for an individual neuron. So that's a constraint that we have to work through in developing the program. So in this case, you can see we have a strain of spikes coming in, and the green ones happen to be ones with positive weights. The red ones have negative weights. And these 2 green ones actually have different values of the positive weight. So each time a green spike comes in, you'll see the membrane potential goes up. Red one comes in, you'll see the membrane potential comes down. There's an additional parameter, which is a leak. With each time tick, independent of the input, we can program the neuron to either decrease its membrane potential, or we can program it to increase its membrane potential, or we can program it to converge towards 0 or diverge away from 0. Many different ways that we can program that leak. In this particular case, it's programmed that if there's no input, the membrane potential will decrease. So you can see as we go along here, we have enough spikes coming in with positive weights, reaches a threshold, generates an output spike, and resets itself. And there are multiple ways we can do the reset. The simple one defined here is when it spikes, it resets back to 0. We can actually set what value it resets to. There are also other resets that enable a more linear behavior where the strength of the inputs defines how many spikes you get out, or you can have it not reset at all. There's an additional rich set of behaviors. The threshold can be stochastic, so each time it's tested, it will vary randomly. The leak can be stochastic, so whether the value of the leak can vary randomly. And the crossbar connections themselves can also be random. So with each spike coming in, we can set a probability that that connection will actually be made. So it makes for a very rich set of characteristics that we can generate multiple things. So in addition to just integrate and fire, we can use just the leak alone to have a neuron generate a spontaneous set of equally spaced spikes. So that can set up to do timing things. We can do control very many other things. And in fact, on the next page, you'll see that it's possible to implement very many different mathematical functions with just a few neurons. Everything shown on this graph was done between 1 and 4 neurons. So we can do mathematical functions, proportionality, summing, generate sigmoid of the output versus the input rates, square roots, and have also replicated commonly known biological neuron behaviors. So very rich set of things that we can do with individual neurons based upon the set of parameters. But again, the key, most important thing is programming in that connectivity, the routing, and the weights that applies to the incoming spikes. We've also developed a GUI simulator of a single neuron that you can use both as a learning tool and to experiment with different neuron parameters. And this is, provides a way to see what's going on. We just see here, we've set it up to just do some simple integrate and spike as we're pulsing at the bottom. And then I think later on it'll show spontaneous behavior, but I'm not going to continue with that. We have that running in the demo outside at the break. You can come and play with this yourself and try different neuron parameters or any one of the many preset different parameter sets that are defined for this. So next I'd like to introduce Steve Esser, who's going to talk about how we actually build real applications by appropriately defining and programming the connectivity and weights.
Thanks. So you've now heard about two of the major building blocks we have in our programs, the neuron and the architecture. One of the main ways that we configure these for specific programs is with training methods. So how do we train TrueNorth networks? Well, from the field of machine learning, we have many different ways for training neural networks. However, out of the box, these methods don't respect the modularity or the discreteness of the TrueNorth architecture. So what we've done, as Brian alluded to earlier, is we've created methods for mapping general neural networks into the TrueNorth architecture. And this in turn lets us take advantage of the large knowledge base that's been created by machine learning already. We found that these techniques work very well for a variety of feature extractor and classifier designs. And as an example, here you can see a Gabor filter. This filter is commonly used in signal processing for extracting oriented edges. And what you can see is we have a real valued traditional version of this Gabor filter on the left. And on the right, you can see that we can produce a viable representation of this filter in TrueNorth by using our mapping methods. Perhaps more important, if we actually apply this filter to the tiger that David showed you earlier, we can see that both filters, both the real valued and the TrueNorth version of this filter, are able to extract similar sets of oriented edges. So functionally, they can achieve the same thing. Now, in addition to this means of training TrueNorth networks, we've also been looking at a second path, a path that treats the TrueNorth architecture as a first-class object. And the idea here is we've actually modified the training algorithm itself so that it can learn within the constraints of the TrueNorth parameter space. The way we typically do this is we start out by pre-configuring the network. An approach that seems to work well is to use a multi-layer design where the lowest layers are responsible for processing local features, the middle layers process regional features, and the last layers are designed to process global features. And in this way, as data percolates through the network, we gradually extract features of increasing complexity. And this also happens to be akin to the way our own brain does visual processing, at least how it's structured. Now, we can get this type of architecture through a variety of means. We can use data-driven approaches, and we can also use topographic approaches, like you see here, where we simply increase the mix rate between cores as we go deeper and deeper into the network. Once we have the network configured like this, the next step is to actually train the synapses. For this, what we're currently doing is using a version of the venerable backpropagation algorithm. I'm sure many of you are familiar with this algorithm, but a short summary. Backpropagation is commonly used today for training many deep networks. Essentially, it works by applying an input to a network, letting that input propagate through the network to make a prediction, and then comparing that prediction to the desired output. That comparison is used to create an error signal, and the error signal is in turn then propagated backwards through the network, and it's delivered to each synapse in such a way that it informs each synapse how much it individually generated or contributed to the overall error. So what we've done is we've modified this algorithm so that it can work discretely and work within the TrueNorth parameter space. Here you can actually see the algorithm in operation training on the NeoVision dataset that you saw earlier. And this is actually the same algorithm that we used to train the highway system that Brian just showed you. And in comparison, the first method I showed you, the method we used to create that Gabor filter, is the same method we used for the tower dataset. So we've actually used both of these in real-world systems. Finally, looking to the future, we're really seeing a whole new field opening up of this type of hardware-inspired learning algorithm. This is really just the beginning of a new field. And the reason we're excited about these algorithms is this. So you've already seen that we can get big advantages in terms of power consumption, power efficiency for brain-inspired systems by moving to the TrueNorth architecture. What we're seeing now is that when we use learning algorithms that are harmonious with the architecture itself, we can build networks that are more compact and more efficient than what we were previously able to do. So we think that by using these two in conjunction, this power-efficient hardware and these algorithms tailored for that hardware, we can start to really push the boundaries in terms of what we can achieve with the scalability and mobility of our applications. Okay, and now I'm going to turn things over to Paul Merolla, who's going to give you an example of building a specific application in TrueNorth.
Thanks, Steve. So you just saw a really important piece of the puzzle, which is that we can learn the parameters of a TrueNorth network directly from data. So now, what I want to show you is a second example of this, except this example is going to be significantly simpler. And specifically, what we're going to do is we're going to train a TrueNorth network to recognize handwritten digits. We're going to do this using the MNIST dataset. If you're not familiar with this dataset, it's a collection of thousands of images of these handwritten digits. Some of them are shown up here. And the goal, of course, is that given a particular image, is to predict what digit is present. What makes this data set somewhat challenging is that people typically find creative ways of writing the same number. So here's an example of two people writing a 7. And if you actually overlaid these two images, you'd see that there's very little overlap between the pixels, and also the features are very different between these. So basically what that means is that there's no simple linear mapping between pixels and between labels. And so you have to do something a little bit more sophisticated, like a multi-layered neural network, for example. So how are we going to do this in the context of TrueNorth? So the first thing to do is to design our network. We're going to pick a very simple network. It's a 2-layer feed-forward network. We're going to use 4 cores in the first layer, and these cores are going to extract features from the image. These features are things like, edges, curves, things like that. And we'll actually learn this, and you'll hear about that later. And the second layer is a classifier layer, and it's just going to use a single core. And what this is going to do is combine those features in the right way to make the predictions. Okay, let's take a closer look now at the connectivity. So the cores in the first layer are going to receive their inputs from local regions of the image. And you already saw this a little bit earlier. So what this means is that the top core, for example, is only receiving inputs from the top left region of the image. And so these neurons are, in a sense, going to specialize or become experts about features in that region. So that layer then will project to this second layer, which is a classifier core. And it's really a convergence going on here. So this core is going to now take those local features that it's discovered and come up with a global prediction for what digit is present. Okay, so you now saw the structure of the neural network. So the next big question is, how are we going to train this? So we're going to do this actually in 2 steps. First, we're going to use unsupervised learning, and we're going to use this just for the first layer to come up with a set of features. And then we're going to use supervised learning on the whole network to do the predictions. So if you're familiar with traditional neural networks, this is a very common technique where you first do sort of pre-training, and then once you find a good set of filters, you do fine-tuning and training on the whole network. And this has been shown to scale actually to very deep networks and very large networks, and one of the reasons why we're interested in. Okay, of course, in our example, though, we're going to have to pull out learning algorithms from the book of TrueNorth. So we're actually going to use another version of backprop. It's very similar to regular backpropagation, except now it takes into consideration the modularity of the cores. So the fact that cores have connections coming in, and in degree 256, out degree 256, it's going to take that into consideration. We're going to use this algorithm for both the unsupervised and supervised learning part. Okay, so how does the unsupervised work? So first, if you focus on the cores in the feature layer, what we're going to do here is we're going to initialize the weights of the neurons in that core to random weights. So if you look here to the right, I'm showing one of those cores, and I'm showing 16 of the neurons. And it's 16 because you can see there's 16 boxes here. So at first, these neurons have absolutely no knowledge about the data set. It just looks like white speckled noise. So now we're going to learn from the data to get better features. So specifically, we're going to use an autoencoder algorithm. So the way an autoencoder works is that you present, oops, didn't mean to go there. You present a digit to the network. A number of neurons will become active. And then you take those activations, and then you try to reconstruct the original image. So in a way, you're autoencoding the input. At first, this reconstruction is going to be very bad because these weights are random. But then we run backprop on this, and over time, the reconstructions will get better. And so you can see, just after even just a few loops through the data, by the way, I'm just showing a few images going through. Of course, there's a lot of training going on under the hood here. And after a few iterations through the data, you start to see that the features it's figuring things out like curves and edges and other things that you would imagine make up the basis sets of digits. Okay, so the next step is once we have these features, first we're going to bring the whole network back. We're now going to initialize this first layer with the features that we just learned. And then we're going to have the classifier core, we're going to start those out again with random weights. And now use supervised learning to figure out how to combine those features in the right way. So of course, before we run supervised learning, the network is going to do a very bad job at predicting these digits. So for example, presenting a 3, the network thinks there's a 7. And so I color it red if it's getting it wrong. But of course, we run backpropagation through this again. And at first, it's going to do very bad. But as it starts to figure out how to combine these features in the right way, it'll start doing better. And when you see that, I think it converges right about now. Yeah, so you start seeing it in green, and it starts making much better predictions. OK. OK, so what you saw in the last talk and in this talk is that we have these training methods to actually take a network of neurosynaptic cores and be able to train them and learn from data. And so this is really exciting because now we can build very efficient TrueNorth programs. This opens up all types of interesting applications where we can take video, image, speech, text, and so on. The network I showed you was, of course, very simple. It was meant to be simple. To put it in context, it actually is just 5 cores, so this would be like 1/10 of 1% of the entire chip. If you want to hear more about this example, we actually have a table set up with myself and Arnon. And so this example is actually a tutorial that we use in SyNAPSE University to try to help people learn and program their first TrueNorth networks. So with that, I'm going to hand the stage over to Arnon Amir. He's going to tell you a little bit about the tooling and the programming environment, which allows us to take these networks like this and actually build a language so that TrueNorth can understand it.